Okay, in this video, we will show the mathematical model of a neuron and also how these neurons can be fit together into a network. In the last video, we talked about neurons being the building blocks of the brain, and the basic configuration of a neuron, which looks like a single central body connected to many other bodies. And we will see the mathematical neuron has a similar structure. Now, let's go back to our regression model and see if we can build on this. Here you have a case with several inputs or several features producing a single output. And this output was a linear function of the inputs. It simply combined the inputs by scalar product with a vector of coefficients. Logistic regression went one farther. It took this scalar product, this linear combination, and applied a function to it. In this case, it was the logistic function. So you can see the similarity between these models, where the logistic model is slightly more complicated. So if we have a regression model with two features, we can represent this graphically as follows. We have three input features. We have three coefficients that we can also call weights. We represent the combination by putting all of the weights into the same node, and then we have a single output. So this was linear regression. We can call this output Z, that's the linear combination. Now, when we did logistic regression, similar structure with weights, but then we applied a nonlinear function to the result. Okay? So we can combine this nonlinear function with a linear combination and represent the combined operation as a single node. Now notice here this x0 is circled in dotted. We'll explain why later, but for now you can just notice it. So if we continue, we simply label this node as A. Now you can see some similarity between the structure of a biological neuron and the mathematical neuron that we've constructed. The x0, x1, x2 reflect the fact that this neuron is connected to a lot of other neurons, which are not shown. The single output reflects the fact that the neuron has a single axon that carries a single signal. Now, this part here is not yet connected, but we will see that we can take this basic structure and connect it to multiple other neurons. I have the potential of taking this output and putting it into other neurons. And we'll see that shortly. Okay, so let's pick up on that point that we can assemble neurons together and develop a more complex system. Now, you remember when we were dealing with regression, we formed complex features. Sometimes we had several features. In this case, we had two features besides the constant feature. And in a case like this, we also took polynomial combinations of features. You can apply nonlinear functions to features and create another feature. So, how do you combine features? How do you create new features? And what degree polynomial to use? So there were many decisions to make. And in some way, we would like to automate these decisions and have the system make them for us. Even for a data set with only two features, if you take polynomial features based on this, if you take powers of x1, powers of x2, if you only take the powers up to order 100, it turns out you get 5,000 different possibilities for features. For example, x1 to the 59 times x2 to the 37 would be a different feature. So if we take combinations of x1 and x2, where we take a power of x1 times a power of x2, if the powers of the individual features range up to 100, in total we can create over 5,000 features. Now this multiplies even more when you have more base features. Right? These are only 2 features. Suppose I have 1, 2, 3, 4 different features. And each one of those features I can raise to a power and multiply together. Rapidly, the number of features explodes. So we want to take advantage of the possible multiplicity of complex features. But rather than producing these features ourselves, we would like some way to develop a system that produces new features automatically and finds the weights and the bias that's appropriate for all of these features. Okay? So a way we can use our existing algorithms to produce new and complex features is illustrated in this slide. Let's take 1, 2, 3 different individual neurons. Each one of these corresponds to 3 base features. We're using the same 3 basic features for each one of these. But the outputs we can treat as new features. Okay? And these features can be plugged in to a second level to be combined. And here we have another neuron. So this mimics the structure in the brain of neurons connected to other neurons. So we can simplify this. As you saw in this slide here, the 1, x1, and x2 are simply duplicated. So there's no reason for me to list the 1, x1, x2 3 times. I simply list them once, and I have the connections. You can see there are 9 connections, where each one of these nodes is connected to each one of these nodes. Now I mentioned before that 1 is circled differently, and this is to indicate that the 1 feature is different from the other features. And the difference is that the 1 feature appears at each level. It appeared here with the first group of features. It appears here for the second group of features. In fact, these coefficients here are called biases. And they're treated somewhat differently from the other coefficients. But we'll see that later. So now we have the beginning of layers, which you may have heard of. Basic neural networks have layers. This is how they're connected. Now we've done this with 2 layers. We can simply add more layers like this. And this is a way to build up complex features. Okay, so we've seen how to model a single neuron and how to assemble these neurons into a network. In the next video, we'll talk about neural network notation.